Hello again, section 3.4. Oops, this says session, session. So does this. That's not right. Section 3.4 is what they meant. And it's asking about inflection points. So inflection points come from the second derivative. And there's a little bit of nuance to knowing if you have an inflection point. So and that nuance is that the point, it must be a point on the curve to be an inflection point. So not only do you have f double prime being 0, but it must exist. It can't be undefined. Actually, it can be undefined. It can be 0 or undefined. Sorry about that. It can be 0 or it can be undefined. And it must be the case that that this is a point on the curve. In other words, that x is, let me say it like this, instead of using x, we'll say at this particular point A, you would know that a comma f of a is an inflection point. I'm saying this all messed up. So let me start again here. The point a comma f of a is an inflection point whenever 1, f double prime at a is 0 or undefined, and it's required that both of them happen too, a is in the domain of f. Both of those must occur. So here's an example. Let me give you an example. F of x is 1 over x, right? It's x to the minus 1. Then f prime of x would be minus x to the minus 2, and f double prime of x would be x to the minus 3, which is 1 over x cubed. So when x is 0, f double prime of x is undefined. So we have a candidate here for where the inflection point could occur. It could occur here, but 0 is not in the domain of f. You see, the graph of this guy would be looking like this. So everywhere in, right here at 0, when x is 0, the curve is not defined. F is not defined at 0, and you can see what the issue is. If you tried to say that an inflection point occurred there, it's not actually a point on the curve. It does change inflection. Here it's concave down, and over here it's concave up. But just because it changes inflection around some x value, there's not necessarily an inflection point there. All right, so let's look at the first question. We have a function t of x, and it's a polynomial, so it will have some inflection points, unless it's a linear polynomial, or I mean, if it's better than, if it's not even, it takes more than linearity. It takes, you can't even, a parabola doesn't have a change in inflection. So a cubic or higher degree polynomial will have an inflection point. Minus 6x cubed minus 7x squared plus 8x minus 3. And even what I just said is not entirely true. An odd degree polynomial where the degree is 3 or higher will have an inflection point, because you could have an even degree polynomial that you know, like x to the 4th. This doesn't have an inflection point, I don't think. Let's check that real quick. Does x to the 4th have an inflection point? So if f of x was x to the 4th, then f prime would be 4x cubed, and f double prime is 12x squared. So clearly when x is 0, we get f double prime being 0. The graph of x to the 4th looks like this. 0 would be right there. I am fairly certain that there's not an inflection point there. This is messing with my definition, though. Give me a second. Well, I guess we would need to go back to our definition. It's not even good enough here, because I would have to add a third thing. So let's call this one number 3 and say that number 2 is that it changes inflection. You could, I guess, eliminate this one from the definition and just say that it changes inflection at some x value a, and that a is in the domain of f, and if both of those things happen, whenever both of those things happen, you get an inflection point. So then it still satisfies this one here, even though there's a change in inflection. You don't have 0 in the domain of f, so it can't be an inflection point. And here, 0 cannot be an inflection point because it doesn't change inflection. Even though it satisfies the idea that f double prime of 0 is 0 and 0 is in the domain, it doesn't change inflection there, so it's not an inflection point. All right, now we're good to go. So looking at this, we need to take the second derivative. So to do that, we need the first one, a minus 18x squared minus 14x plus 8, and then t double prime, it would be a negative 36x minus 14. All right, t double prime is a linear function, so it's defined everywhere. Then the only x value we're concerned about is if it's where it's 0. And so this thing will be 0 when x is negative 14 over 36. I know that because if I took that number and put it right there, the 36's would cancel, the negatives would make it positive, and it would say 14 minus 14. And then this number will simplify because 14 is 2 times 7, and 36 is 2 times 18. Okay, so let's do this. Let's draw a little number line and put on there the minus 7 over 18. Now this is a negative slope line, so it's going to go down like that, which means just that it's negative over here, but it's positive over here. The y values are positive, so it would be concave up here, and it would be concave down here. All right, and if we had done the same thing on this one, we would have seen that on either side of 0, this function 12x squared is positive on both sides of 0, so it's concave up on both sides. It didn't change inflection. All right, so we have an inflection point at minus 7 over 18, comma, t of minus 7 over 18, and I suppose they're going, no, they're not going to want me to put that point. They're just asking me for the x value where it occurs. So that's at minus 7 over 18. Here's another one. Use the second derivative test to find all the x-coordinates of all local maxima. And if there are multiple values, give them separated by commas. Okay. Well, that second derivative test means so actually I think they've used the wrong words there. In my mind, the second derivative test is the test for concavity, but I know what they're wanting. They're wanting me to use this more elegant method of determining local minimums and local maximums. If you remember, the first derivative test had us take one derivative, the first derivative, and determine that if the tangent line, where it was 0, and if the tangent line was 0, you know, we'd make a number line chart, and if the tangent line was 0 at this point, but it was decreasing and then increasing, well, then it made a local minimum right there at A. But there's another way to do it, and that is to check the concavity at the critical values. So if I find Q prime, it would be 11x to the 10th minus 30x to the 9th. Okay. And so I'm needing my critical values. And to do that, I would have to factor it. So I'd factor out an x to the 9th and be left with 11x minus 30. Okay, so my critical values would be 0 and 30 over 11. Now, if I take a second derivative, I get 110x to the 9th minus 270x to the 8th. And I want to check the sign of each of these critical values in the second derivative, because this will tell me that so this is a critical value. It's a potential place where it's exactly where the tangent line is horizontal, and all we're doing is verifying that it doesn't do something like this. Because if it does something like that, then the tangent line was horizontal right there, but it changed concavity. However, if the curve is doing something like this, then the tangent line is horizontal right there, and if I get that it's concave up at that critical value, then I know that it makes a local minimum. And likewise, if it was concave down at a critical value, then I know that it makes a local maximum. So, well, if I put 0 into here, I can't learn anything, right? I get 0 minus 0, and I don't truly know if then my second derivative test is inconclusive. But if I put this positive number, 30 over 11, into here, then Q double prime of 30 over 11, let's see. Well, this is 11 times 10, and then this is 30 over 11 to the 9th power. Actually, let me factor this thing so I can make better sense of it without having to get my calculator out. So this is x to the 8th times 110x minus 270. I can do better. This is 10x to the 8th times 11x minus 27. Then this would be 10 times 30 over 11 to the 8th power, which is some massively positive number. But the question is, will it be times this negative number? No, it won't, because you would have 11 times 30 over 11 minus 27. And you can see that all three of these numbers, all three of these factors, here's one of them, that's positive. This is a positive number, and this is a positive number, because the 11s cancel and it says 30 minus 27, which is positive. And so I know that it would be concave up. It will be concave up at 30 over 11, so it makes a local minimum there. And the only question is about what's happening when x is 0. And you can see from the sorry, let me recap here. So this is positive, so it's concave up, which means we have a local minimum. And the question is asking us for local maximums. So a local maximum will not occur here. Well, then we have to backtrack up to our first derivative and look at the sign chart for it. Now, this is the first derivative, so you can see it has two roots, one at 0 and the other one at 30 over 11. Now 30 over 11 is a positive number that's bigger than 1, so I'll use a test value of 1. And I can see if I put a 1 in here, it would be positive, and if I put 1 in here, it would be negative. So it's negative right there, and because this is an odd degree, it will alternate signs at each of those critical values. So then you have the function q is increasing here and decreasing here, and it has a horizontal tangent line at 0. So then the answer is 0. 0 is the only place where you have a local maximum. All right. We have a function g of x. They want to know if at this x coordinate of 2, is it concave up or concave down? All right. Well, to determine the concavity, I should take the second derivative. So this is minus 27x squared plus 18x plus 1. And the second derivative would have a minus 54x plus 18. Now that second derivative is a line, and the potential candidate for a point of inflection would be the point 18 over 54. And I can see that because if I put it right there, the 54s would cancel and it would say minus 18 plus 18. And this 18 over 54 simplifies in multiple ways, because 18 is 2 times 9 and 54 is 2 times 9 times 3. So this is just 1/3. Okay, then here at 1/3, I know that that this line must change from being positive to negative at 1/3 because it has a negative slope, so it's going down like that. This would be the graph of that line G double prime. And that's just telling us that the concavity is positive here, but it's negative over here. So it's concave down there and it's concave up over here. And at the x coordinate of 2, 2 is living over here, so it's concave down when x is 2. Find all local minima of the following function. Okay, well that was a quadratic function. So it looks like this. Now the second derivative here is going to be a constant. In fact, it's just going to be the number 2, because h prime would be 2x minus 5, and h double prime would just be the number 2. So it's concave up everywhere. And then that means that for my critical value of 5/2, and I can see that that's a critical value. If I put it right there, the 2's cancel, and it says 5 minus 5. So at the critical value of 5/2, it is concave up. Then therefore it has a local minimum. It's concave up at 5/2, so it has a local minimum at 5/2. All right, here we have a graph of f prime. Find all of the intervals over which f is concave up. All right, neat question. Let me get a picture of it on my sketch pad here. Okay. So let's label this carefully. You can see it right there. They called it f prime. This is f prime. So this thing is describing the slope of the tangent line of f. And they want us to select all of the intervals over which this thing is concave up. Now it will be concave up at wherever the second derivative is positive. Excuse me, yeah, positive. To be concave up, it must be the case that the second derivative is positive. Now, the second derivative of f is the derivative of f prime. So if I'm looking at f prime and I'm studying its tangent lines, this thing doesn't have any positive tangent lines. And since it has no positive tangent lines, there can be no place where the derivative of this curve so let's do it like this. Let's call this thing G. Let's call this thing G of x. And we can see that G of x has no positive tangent lines. Well, that tells us that G prime of x is negative everywhere for all x values. But if G of x is equal to f prime of x, then that means that f prime of x, that the derivative of f prime of x is less than 0 everywhere, and this writing is just the second derivative of f. So it doesn't have anywhere where it's concave up. Here we have a graph of f prime, and they want to know over what intervals is f concave down. Okay, let's get a picture of this on my sketch pad. this is f prime, I'd be curious about where is the tangent line to this curve? Where are the tangent lines having negative slope? Where are the tangent lines having negative slope? Well, that would be from 0 to infinity. So everywhere in that interval, you would have that f double prime of A is less than 0 for any A in the interval from 0 to infinity. Analyze this graph of f. Select all the intervals over which the function is concave up. Okay. Well, I need to make a little sketch of this, I guess. Or I need to draw on it to illustrate where that happens. So you have an inflection point here and here. Because in between these dashed lines, it's concave down, but on either side, it's concave up. So you'd have from minus infinity to what appears to be 1/2, together with 3/2 onward to infinity. And we're supposed to pick all that apply. Select all the intervals over which it is concave up. Okay, I understand the question. So, they're not asking me to produce the interval over where it is concave up. They're asking me to pick from this list whichever intervals satisfy the criteria that it is concave up at these intervals. So from negative infinity to 0, it is concave up everywhere in that interval. And from 0 to 1/2, it is concave up in that interval. But from 1/2 to 1, it is not concave up. And from 1 to 3/2, it is not concave up. But in these two places, it is concave up. Now, why they didn't include 2 and 0, I am unsure, because I would argue that it is concave up at both of these local minimums. Let's see. by our definition of concavity, so this is why they had to exclude those. They're strange definition. I don't really, if f prime is increasing, I mean, you're going to tell me that it's not concave up when x is 0. I think you're wrong, because it absolutely appears to be concave up there. And that just illustrates that there's a problem with this strict definition to say that f prime must be increasing on that interval. Well, f prime is not increasing when x is 0. F prime is equal to 0 there. To be increasing for the function, for f prime to be, actually hold on, f is concave up on an interval if f prime is increasing over that interval. All right, so I had to think about this for a minute, and I have written my complaint to Newton, and let's look at what's going on here. So this was their statement, and it turns out that this definition they've given is just fine. You just have to read it carefully. F is concave up on some interval if the derivative is increasing on that interval. Okay, well, I've drawn some pictures here. We have our original curve, F, this is F, and then so I've got a sketch going of F prime. So here's F prime, and you can see that F prime is increasing everywhere to the left of 1/2. And it's increasing everywhere to the right of 3/2. So since f prime is increasing in both those places, then by the definition you have that it is concave up from negative infinity up to 1/2 and 3/2 to infinity. Now, I went ahead and sketched a picture of f double prime that would correspond to this f prime, and you know, just by looking at where f prime would be 0, it would be 0 here and here, and it's positive, you know, in both of these intervals. And this boils down, this definition boils down to the same, it's the same exact thing as saying that the second derivative is positive. That's what it means to be concave up. If this is positive, that's the same idea as f prime is increasing. So it's precisely the same. And so this definition is fine. However, their error is, you know, right in here. Now you can see that they got the same interval that I got down here, because that's the correct interval. However, this statement that they've made is not right. The statement is not right, and I've written a letter here to tell them that it's not right. Let me add that, well, I'll add it in a second. So you can see here that what I've said is that, you know, your statement is not right. What we can see is not that the slope of the tangent line is increasing. Slopes, it doesn't matter if the slope is increasing. Well, I mean, you can determine something from looking at if the slope is increasing, because if I look here at this graph, then I've got some slope here, and boy, look at how that slope just keeps increasing right up to the inflection point. so the slope is increasing. That can be said, and if the slope is increasing, then it will be concave up. That part, I guess, is true. However, I guess then the objection would be here, and thus the value of f prime. Well, so I guess I have an even easier way. Look, this explanation is just way too sophisticated. It's taking me a minute to dig through it. It would be true that if the slopes are increasing, you are concave up. That's true, because once the slopes start to decrease, it's concave down. And it's the value of f prime. Well, I guess the value of f prime is increasing. So, I mean, because that's the same thing. If the slope is increasing and the value of f prime is increasing, that means the same thing. And the value of f prime increased to a maximum here. Let me think again for a minute. All right, well, I guess I changed my mind. The problem here, I guess, is me. I just do not like what they have said. There is far easier ways to understand concavity, namely that it's concave up wherever the second derivative is positive. But the second derivative being positive literally means for you that the first derivative is an increasing function on that interval, but I claim there is a distinction between being an increasing function and the function value increasing. Because you can have functions like this, that look, the function value has increased, but it is not an increasing function. I think I'll just keep my comment to myself, and then we can just move on. So this statement down here at the end is correct. Notice how it contradicts 0 and 2. They never claimed that all of these intervals union together would comprise the entire collection of points where it is concave up. They should have, so I don't know why they have excluded those, and I'm not going to ask. All right, let's go on to the next one. Select all of the intervals over which the function is concave up. Okay, so that's going to be everywhere except at -3 and 0. So it's going to do it there, and well, and I guess also at -2 and -1, because those would also be so actually I've misspoken. So let me get a picture of this. If I look at where it appeared that it was about to change concavity, actually no, my words are fine. So in between here and here, maybe it's not even at -2. Maybe it looks like almost there. Here it's concave down. And in between here and here it's concave down. But everywhere else it's concave up. So I want to exclude these intervals. Okay, then I would have to pick zero to infinity and this one. So these are the three, these are them. Yikes. Is it concave up or down at the point with x coordinate -2? It's a cubic function, so g of x is 4x cubed plus 9x squared plus 7x plus 3. And g prime is 12x squared plus 18x plus 7, and g double prime is 24x plus 18. And so at -18 over 24, you would have an inflection point, because this is a positive slope line. It's going up like that, so it's positive over here, negative over here. That means it's concave down and concave up, or F is G is concave down and concave up right there. And -2 belongs in this region because this is not even -1, and so it will be concave down right there. Now you could stick -2 into the function g double prime, but you're going to learn the exact same thing. I don't like to do that because I don't actually care if that this number is -30. I only care that it is negative. And I can figure that out without having to explicitly find the number. We have another cubic. Find the x coordinate of the inflection point to P. Okay. Well, P of x is 8x cubed minus 7x squared minus 6x minus 3, and these two things don't even matter at all because they're going to be gone by the time I do the second derivative. So P of x would be 24x squared minus 14x minus 6, and that part's gone to 0 now, and then when I do P double prime, the minus 6 will be gone, so I'll have 48x minus 14. Then the value of 14 over 48 is what I'm interested in. And being that this is a line, being that P double prime is a line with positive slope, then its graph would look like that. So that means that my concavity is positive here and negative here. It's concave down and then concave up. And 14 over 48 will simplify because 14 is 2 times 7 and 48 is 2 times 24. and the 2's cancel. So then the x-coordinate of my inflection point is 7/24. Find all of the x-coordinates of the local minima. So let's do it. We have q of x being x to the 4th minus 4x squared plus 10. Q prime, so q double prime will be a quadratic, right? We'll have to factor it. Q prime is x cubed, is 4x cubed minus 8x. And I want to know the critical values there, so I should factor out mx. Actually, I'll factor out a 4x, and then have the remaining term of x squared minus 2. So then my critical values are 0 and plus or minus the square root of 2. And I want to check in q double prime the sign of those numbers. So this would be 12x squared minus 8. And that would in turn tell me that if x were 8/12, well, I'm sorry, if x were not 8/12, sorry, that's not a linear function. I should factor this, and I can factor out, I guess, a 12. Let me factor out a 12 to make it simple. Then I would have x squared minus 8/12, and 8/12 is 2 times 4 over 2 times 6. Or actually I should say 2 times 4 over 3 times 4. So the 4's would cancel, and this would just be 2/3. Okay, then my potential inflection points are plus or minus square root of 2/3. Okay, this is a quadratic that faces up, so its graph looks like this. That means it's negative here, positive here, and positive here. So I'm concave. So Q, excuse me, is concave up and then down and then up. Okay, so it does all this concavity changing stuff, and my critical values here, I now know everything that's going on, because there's 0 and square root of 2 is over here, and negative square root of 2 is over here. And they're asking me for local minima, so the local minima will occur at plus or minus root 2. Here's the cubic function, and they want, again, the local minima. Okay, so that cubic function is, sorry this is such a long video, we're almost done. This is probably the last question. X cubed plus 5x squared plus 10. All right, so P of x would be 3x squared plus 10x, which factors like this. So then my critical values are 0 and a negative 10/3. All right. And this was P prime. Now P double prime would be 6x plus 10. And so the value I'm interested in would be a negative 10/6. Or I guess I could call that a minus 5/3, because 10/6 is 2 times 5 over 2 times 3, and the 2's cancel. So here at negative 5/3, this is a line with positive slope, so it goes up like that, which tells us that P is concave up here and concave down there. And now 0 would be living over here, and negative 10/3 would be living over here. And which one of those has a minimum? It's 0. All right, and we are finally finished. See you in the next video.